time to talk about another exam. We're talking about Calc 2, also known locally, Math 166. A beautiful vintage, fall 2023, and it's the third exam. That means we're talking sequences, that means we're talking series, that means we're talking Taylor stuff. Wow! It's gonna be fun, right? Well, that's what we keep telling ourselves. But you know what? It really can be. Oftentimes this gets the reputation as like the hard exam. But we can do this. We have the skills. We've been practicing. So let's go through and let's talk about what's going on. And of course we put our name, because otherwise how are we going to get the credit? Well, let's begin. Number 1. We have the function f of x, which is 2 times square root of x minus 3. And we're told, write the Taylor polynomial of order 3 generated by f of x at a equals 7. Okay, so there's a couple of things we need to make sure we understand. What do we mean by order 3? What is this a? So let's remind ourselves, what are we talking about when we talk about Taylor polynomials? Well, probably the simplest Taylor polynomial that we know, and that we've spent some time working with, is the tangent line. So the tangent line is a Taylor polynomial. Now the goal of the tangent line is to do what? It says, hey, locally our function looks kind of like a line. And we can use that to understand the behavior nearby. So Taylor polynomial says, well, why stop at line? Let's use more information and get a higher order polynomial. And so if we use information about the second derivative, the third derivative, and so forth and so on, we can get a better approximation locally. All right, so what does the order tell us? Well, basically it says, how much information are you using? So because it says order 3, we're going to go up through the third derivative. What is the a? That's where we're getting our information about the function. So you might say that's the center of the Taylor polynomial. So in general, what we have is that the Taylor polynomial is an approximation to the function. So we say, all right, so we have our function is approximately, and I'm going to use the sum notation for right now. So we're going to add up starting at 0 and going to somewhere. I'm going to hold off on that. And then we're going to have what? Well, it's going to be our f, the kth derivative at a over k factorial times x minus a to the k. Now, let's give this a name. All right, we'll call it L. Now, there's two important things. What's A? What's L? So this L, what you see here, this is our order. So in other words, how far do we go? The higher L is, the better the approximation. The A, and it shows up in two places, that's where we're centered. So in our case, we have L is 3, A is 7. All right, so that is to say that for us, and remember these are all approximations to f, we're going from 0 up to 3, the kth derivative at our point 7, divided by k factorial, never forget that k factorial, x minus 7 to the k. Or if you write that out, well, when you plug in 0, 0th derivative, it's just another name for the function. So it says take f of 7. Then you have the first derivative divided by 1 factorial. All right, well, that's f prime of 7. And then you're going to take times it by x minus 7 to the 1. Well, we did multiply by x minus 7 to the 0. X minus 7 to the 0 is 1. Okay, so that's why we didn't write anything down. X minus 7. All right, now we go to k equals 2. So that's the second derivative. We divide by 2 factorial, which now is interesting. It's not 1, it's 2. And times by x minus 7 squared. And finally, for 3, that's the third derivative. We're going to divide it by 3 factorial, which is also, I guess we should have said 6, and times by x minus 7 cubed. Okay, good. So what do we need? Once we have the form, then the next big thing to do is to say, well, what are all these derivatives? And in particular, what happens when we plug in 7? So let's pause here, and we're going to do some work with our function. So we'll say, well, f of x, that's 2 squared of x minus 3, but we're going to write that as x minus 3 to the 1/2. That makes it more calculus friendly. So the first derivative does what? Well, the 1/2 comes down. 2 times 1/2 is 1. Well, that's nice. We have x minus 3 to the 1/2 minus 1, which is negative 1/2. And then the derivative of the inside is 1. Okay, so there's a times 1, but we'll say, aha, we know how to times by 1. Next, the second derivative. Well, all right, that would be minus 1/2 x minus 3 minus 3/2. Right? Bring the power down, subtract 1. And again, the derivative of the inside is 1, so there's a times 1, but we'll not write the times 1. So, last step. Minus 1/2 times minus 3/2 is 3/4. We have x minus 3 to the minus 5/2. And again, times 1. Okay, well, we're not plugging in the functions, we're plugging in the functions at 7. So we're now going to take each one of these, and we're going to plug in 7 and see what we get. So let's start with the function. Well, we have that f of 7 would be equal to 2. 7 minus 3 is 4. Then 4 to the 1/2 means square root of 4. Well, 2 times square root of 4 is 4. All right, that's not too surprising. F prime of 7, well, you have, this is 4 to the minus 1/2. So that's really 1 over square root of 4, and that means we get 1/2. All right, f double prime of 7, well, what do we have? We have minus 1/2, and then we have times 4 to the minus 3/2. So 1 over 4 to the 3/2. Now, how do you do 4 to the 3/2? Well, you could say, well, we know 4 cubed is 64. Square root of 64 is 8. So that's 8. Another way you could do it, which is probably easier, is think square root of 4 is 2, and then 2 cubed is 8. So this is 1 over 8 times minus 1 over 2 makes minus 1 over 16. All right, last one. F triple prime, the third derivative. Okay, we have our 3/4. 1 over 7 minus 3 again is 4 to the 5/2. Well, we could, of course, take 4 to the 5th, which we all know is 1024, and then the square root of 1024 is 32. But we probably are easier to say, oh, wait a second, square root of 4 is 2, right? And then, yeah, okay, then 2 to the 5th, so that's 2, 4, 8, 16, 32. All right, so we have a 32 there, times 4 makes a 128, so we have 3 over 128. All right, so there's our derivatives. We're almost there. We're in the home stretch. And so now we go back, we say, okay, so our Taylor polynomial, that's our piece here. So we start replacing things. Say f of 7, 4, all right, plus f prime of 7, which is 1/2. So plus 1/2 x minus 7. F double prime of 7, divide by 2. Well, okay, so that's negative 1 over 16 divided by 2, same as multiplied by 1/2. We'll make this minus 1 over 32 x minus 7 squared. All right. Then we have plus, and well, what do we have? Well, okay, maybe we'll do a little computation on the side. We have f triple prime of 7 is 3 over 128, and we're dividing by 3 factorial, so that's 1 over 6. Well, of course, we can cancel a factor of 3, and then we have 128 times 2, 256, powers of 2. We love our powers of 2. So plus 1 over 256 x minus 7 cubed. And because we're third order, that's where we're stopping. And we're done. That's it. We don't want to expand, well, because one, that takes work and might introduce algebra errors. But more importantly, the moral is we're really trying to understand what happens near 7. And so rewriting it really loses that. Leaving it in terms of x minus 7 is great, because now if we were to do something with this, for example, we were to evaluate, say, oh, plug in 7.1, here it's really easy to plug in 7.1. Whereas if you expanded it and then tried to plug it in, uh-oh, trouble. All right, so when you're dealing with Taylor polynomials, don't want to do your expansion. Just want to make sure you know how far to go. Make sure you don't forget about your k factorials. Make sure you plug in your functions, right? We don't plug in the functions, we plug in our functions that have been evaluated at our point. But the moral is, we can do this, right? It's just like tangent lines plus plus, right? Just keep going until you have enough terms. All right, there we go. Off to a great start. On to the next problem. Number 2. Consider the sequence of terms given by a sub n. So a sequence of terms just means we have a long collection of terms, infinitely many terms. The a sub n means that it's the nth one, so it depends on n. And in particular, it's n minus 3n squared over 4n squared plus 2 root n. And now we're saying, okay, give a sub 100. All right, well, what's that? Well, it means what you do is you say, if I want a sub 100, everywhere you see an n, you put in 100. All right, so we say, okay, a 100 is, wherever I see an n, I put 100, so 100 minus 3 times 100 squared over 4 times 100 squared plus 2 square root of 100. Now you could say, yeah, there we go. All right, well, let's see if we can't clean it up. 100 times 100. Well, essentially what you're doing is when you multiply by things which end in zeros, you add more zeros. So if we think about this, 100 squared would be something with 4 zeros on the end. So that would be like 10,000, because it is 10,000. So we can say, okay, so this is like 100 subtract 30,000, right? Because 3 times 10,000 is 30,000. Lots of zeros. And downstairs, 100 squared, again, 10,000. So you have 40,000. And then square root of 100 is 10 plus 20. Now the downstairs is pretty easy to add those. It's 40,020. What about the upstairs? Well, it's maybe a little easier to think about as 30,000 subtract 100. So, oh, okay, well that's just a little bit short of 30,000. That's 29,900. But you have to say, aha, we sort of swapped what we were subtracting, which means it's the negative of that. So negative 29,900 over 40,000. All right, now there's a part 2 to part A. So it's like, wow, it's a part within a part. Interesting. This kind of feels like an inception of problems, right? There's something, another layer going on here. Does the series converge or diverge? Ooh, already getting to questions about convergence or divergence, and we're only on part 2 of part A of number 2. Well, okay, let's think about what's going on here. Let's actually think about the terms a sub n. Now, as we look at these terms, I see addition and subtraction going on. And whenever I see that, I say, okay, I should focus on what's the important term. In other words, I like to think of it as get rid of the noise. There's distractors here. So what's the important stuff upstairs? In other words, what grows the fastest? The n squared or the n? Well, the n squared grows fastest. What about downstairs? It's n squared or root n. Well, again, the n squared. So really, when we think about this, we say, okay, this is approximately minus 3n squared. We're just looking at the highest power stuff over 4n squared. And we say, oh, wait a second. once you eliminate the lower order terms, get rid of the noise, the higher order terms are the same rate of growth, which means that for large values of n, it looks like -3/4. And that actually seems about right here, right? This is really close to -30,000 over 40,000, which is like -3/4. Now, how does that help us? Well, here's the thing. We're adding up a lot of terms, and most of them are very close to -3/4. So when we go far out into the series, it's like plus -3/4, plus -3/4, plus -3/4. And so if you add up a lot of stuff that's not getting close to 0, it's going to blow up. And so we can see it's going to diverge. So the answer is that this diverges. And why? Well, because we have to justify. You know, if we just say diverges, that's maybe a point. It's the justifying. That's where the real points come into play. We want all those points. We love our points. And what's our justification? Well, there's something called the basic divergence test. And what that says is, hey, what's happening to your terms? And what's happening is that a sub n is going to -3/4, which is not 0. So if your terms don't go to 0, your series must diverge. And now this is very particular here. It's a great way to test if something diverges. It tells you nothing about whether it does converge, because there are times when the terms go to 0, but it still does not converge. So be careful about what the test says. All right, so remember, basic divergence test. If you don't go to 0 with your individual terms, you can't converge. That's all we can conclude. All right, so that's part A. Part B. Consider the sequence of terms given by b sub n is n log 1 minus 4n. And now we're asked to find the limit as n goes to infinity b sub n. And okay, we want to give work to support our answer. Well, let's see what's going on. So we have our limit as n goes to infinity, okay, of b sub n. Well, that's the limit as n goes to infinity of n log 1 minus 4 over n. Now, what you do is you plug in. Now, of course, you can't plug in infinity, but you can say, well, what would it look like at infinity? What is this going to? And we say, well, this is going to infinity, right, because n is going to infinity. Then this 4 over n is going to 0. And then you say, oh, well, 1 minus 0 is 1, and log of 1 is 0. So it's infinity times 0. What does that mean? Infinity times 0 means more work, more work. And so it's what we call indeterminate. That's right. And so we have to determine it. And in particular, what's our favorite tool when we have indeterminate things? It's L'Hopital. L'Hopital, mon ami. All right, so we get to do L'Hopital. Okay, so now if we're going to do L'Hopital, and we're going to do it properly. Say, okay, we have to first make it look like a fraction, because it needs to go to something over something. So we say, okay, we have to move something downstairs. Now there's two candidates. There's the n piece and the log 1 minus 4 over n piece. What moves? Well, I would say move the n piece down, because this is, you don't want 1 over log. They're just going to get more complicated. But whereas when you take rid of just log, the log part goes away. So that's why we're going to move the n part down. All right, so let me see what happens here. So we're not doing L'Hopital yet. We're first preparing. So the limit as n goes to infinity. And then we have log 1 minus 4 over n over 1 over n. Because you move the n part downstairs, it flips over. So if it was n over 1 upstairs, it's 1 over n downstairs. Now, of course, let's do our check. Now what's happening? Well, the log term upstairs goes to 0. Great. How about this 1 over n? It goes to 0. Now we're ready for l'hôpital. Ah, yes, l'hôpital. Okay, so what happens next? Well, this becomes, and we'll mark this with l'hôpital, the universal LH, and says, okay, this becomes limit. N goes to infinity. We're going to think of taking the derivative with respect to n. Well, we'll start with the downstairs. 1 over n, that's like n to the minus 1. The minus comes down, then you have n to the minus 2, so that's 1 over n squared. All right. Now, log. Okay. I did not give myself enough room. But, okay, so it's 1 over the inside. Okay, so 1 over 1 minus 4 over n. And we're going to times that by the derivative of the inside. All right, well, that's 0. Then you have minus 4 times derivative of 1 over n, which is minus 1 over n squared. Now, the nice thing is, the minus 1 over n squareds cancel. Nice. All right, so we're just going to go pshoo, pshoo. Okay, now what do we have at this point? Well, we have the following, and this says this is equal to the limit. N goes to infinity, and we have minus 4 over 1 minus 4 over n. All right? And, okay, great. Well, what happens? Well, what does happen? What we see here is the 4 over n goes to 0. Aha! Cool. And so we end up with minus 4. All right. And there you go. There's our answer. All right. Well, cool. And another problem down, right? Yes. And, well, let's keep going. Number 3. Consider the series. So we're going from 1 to infinity, and then n to the minus 1 means it's like a 1 over n upstairs, and downstairs log n squared plus 1. Okay, part A. State the 3 required conditions for the use of the integral test. All right, well, what do we need? And so we have a sum, n equals k to infinity of f of n, f of n, and well, we need a couple things to be true. We need that f of n is positive. We need that f of n is decreasing. And we need that f of n is integrable. And, well, one way you can make things integrable that is very simple is continuous. So those are the things we're looking for. Is it non-negative or is it positive? Is it going down? And is it integrable? So we'll just say is continuous. Okay, so if we have a sum of a function of n, so here, this part right here, this is our f of n. And in particular, where we think of f of x is what? Well, x to the minus 1 over log of x quantity squared plus 1. Okay, so there's what's going on. Now notice part A is just completely general. It's actually not tied to this particular problem. It's really saying, hey, do you understand the integral test? Oftentimes we apply things, but we may forget about conditions. But now we're going to go into the applications. So part B, use the integral test to determine the convergence of the series, providing justification as to why the series converges or diverges. You may assume the series satisfies the requirements. In other words, we don't have to show that we're positive, decreasing, or continuous. And, you know, some of these things are easier than others. Showing that it's positive is pretty straightforward. Showing that it goes to 0, not too bad. It may do some really weird stuff at the start, but you know what? when we talk about convergence or divergence, weird stuff at the start doesn't bother us. It's the end. You always care about the end. So we're looking to the tail. We're like saying, hey, what's going on down there? And we're saying, okay, if what's going on down at the end is like, oh yeah, it's nice and behaved, life is good. Continuity, by the way, very easy because these are nice and continuous functions in the range that we're interested in. Okay, so what's the punchline? The punchline says, instead of looking at the sum, what we're going to do is we're going to look at the integral. Say, okay, we're going to compare with the integral. Now, they're not the same value, but you can glean information. Now, this x to the minus 1, I'm going to write that as a 1 over x, just because I like x to the minus 1 as 1 over x when I'm doing calculus, because it really reinforces, like, oh, I recognize 1 over x. 1 over x is the derivative of natural log. And so when I see x minus 1, it's like, well, that's 1 over x. Okay, so the punchline is whether or not this converges is the same thing as whether or not this converges. And they're not, as I said, the same value, but they're actually a little bit close. And that's the whole punchline. We can use the integral test to actually get some bounds on behavior if we really wanted to and did some work. But we're not asked to do that. Okay, so we're now considering this integral. Well, the 1 over x is suggestive. We say, all right, well, let's let u equal log x. Then du is our 1 over x dx. Say, ah, cool. We have a 1 over x dx. This is going to become our du. So this is the integral of, we have a du, and then we have a 1 over u squared plus 1, and we have to talk about our bounds. Now, these are x bounds. X goes from 1, x goes to infinity. We're going to u bounds, so we have to change. Plug in x equals 1. Log of 1 is 0. So we start at 0. Infinity, well, you plug in infinity, which really means what happens as you go to infinity, and log as you go to infinity goes to infinity. It takes its time and goes very slowly, but it does go. So, okay, to infinity. Say, all right, cool. So now what do we have? Well, we have an integral that we can do. In fact, between you and me, don't tell anybody, this is one of my favorite integrals. It's arctangent. Ah, what are the odds? Well, pretty good. Problem writers love arctangent. And okay, now you plug in infinity, and you say, well, what happens as arctangent goes to infinity? There's an asymptote. It goes to pi over 2. And then plug in 0, arctangent of 0 is 0. Now, our answer isn't pi over 2, because the question is, does it converge or diverge? And we say, well, we had the sum, we changed to the integral converged. And so here's the punchline. They have the same behavior, not the same value. So we say, okay, this converges, that's the conclusion, since by the integral test, the integral from 1 to infinity of 1 over x, 1 over log x squared plus 1 dx converges. And when we say an integral converges, it means it goes to something finite. And so that's our conclusion. So when we're doing a justification of using the integral test, you say, hey, what happened to the integral? Did the integral converge? Great, then your sum converges. Did the integral diverge? All right, well, then your sum diverges. And there we go. All right, good. 3 problems down. Let's keep going. Number 4. We're asked to determine the interval of convergence of a series. we're going from 1 to infinity, negative 1 to the n, x minus 2 to the n, over n to the half power 4 to the n. And we're told to justify our answer. Okay, so interval of convergence is going to go in 2 rounds. First round is radius of convergence, which tells us everything except 2 points. And those are our endpoints of the interval. And so round 2 is what happens at those 2 points. Okay, so first off, let's talk round 1. So round 1, and here we're talking our radius. And when we're in round 1, we always do one of 2 things. And it's always one of these 2 things. And it's either we're going to do a root or a ratio test. And so we have to decide which one we're going to do. And how do you know? Well, here's the rule of thumb. If you see a factorial, you have to go ratio. If you don't see a factorial, lean towards root. And so, no factorial, we lean towards root. The other thing is lots of things to the power n. So we say, okay, all right. So we're going to think of this right here. This is our a sub n. And we're just going to think of x for the moment as being fixed. So applying the root test, we're going to take a limit as n goes to infinity of the absolute value of a sub n and the nth root of that. And we want to see what this becomes. So first off, we say, okay, that's the limit as n goes to infinity. And we're taking absolute values. So you'll notice the minus 1 to the n, absolute value, it makes that go away. So we have upstairs the absolute value of x minus 2 to the n. Downstairs, n to the 1/2, 4 to the n to the 1 over n power. So that's our limit as n goes to infinity. And now we bring in our nth powers. So we have our absolute value of x minus 2, the nth power and the 1 over nth power completely undo each other. Downstairs, well, 4 to the nth to the 1 over nth becomes 4. And then we have n to the 1/2 to the 1 over n. Now, we're going to actually swap those. So we're going to think of this as n to the 1 over n to the 1 over 2. And the reason we're going to do that is we're going to say, hey, what's going on? Well, there's some side note here. The only place we have n's right now is right here. And we say, oh, you know what? We noticed something. Namely that the limit as n goes to infinity of n to the 1 over n is 1. And so we say, ah. And since that only place that we have n showing up is right there, we say, well, that's going to 1. And so our limit is absolute value of x minus 2 upstairs. 1 to the half is 1 times 4 is 4. Now, let's recall the root test. The root test says we care about when this converges. And this will converge. If this is less than 1, it absolutely converges. If this is greater than 1, it diverges. And then if this equals 1, we don't know. And so that's why we're doing this test. By the way, this is the same for the ratio test. And now our great aha, we really focus on the less than part. We say, okay, so we now know for sure that this will converge when we have our absolute value of x minus 2 over 4 less than 1, or if you like, absolute value of x minus 2 is less than 4. Okay, cool. Cool. So, picture, let's update where we're at. What we know is if we start at 2, then we go 4 in each direction. So 2 plus 4 will get us out here to 6. 2 minus 4 will get us out to negative 2. We are converging in between those two. So from -2 up to 6, we are happy. That's converging. Life is good. By the same kind of argument, when we're outside, we're out. So it's not going to work below -2 or above 6. Well, we're not done for the interval because we have round 2, which are these 2 points. Okay, so now we're ready for round 2. And for round 2, that brings us to our endpoints. And, okay, great. So what do? Well, now we're going to actually plug in our values for x. So we have 2 sums we have to figure out. And on a spoiler alert, for sure, root and ratio tests are useless in round 2. If the root or ratio test answers the question in round 2, mistakes were made. All right, but I'm getting ahead of the story. So let's plug in -2. So this becomes the sum from 1 to infinity of -1 to the n. -2 subtract 2 is -4 to the n over n to the 1/2, 4 to the n. Well, -1 to the n, -4 to the n, that makes 4 to the n. Upstairs, there's a 4 to the n. Downstairs, this is sum n equals 1 to infinity of 1 over n to the 1/2. And we say, oh, p series. And in particular, what's our exponent? 1/2. And that means this diverges. Okay, so that is not in our interval. So -2 is a proper full circle. It's not part of our interval. Okay, so we don't include -2. What about our other endpoint, which is 6? Okay, similar process. 6, again, plug it in. Sum n equals 1 to infinity. We're going to have -1 to the n. 6 minus 2 makes 4 to the n. Downstairs, n to the 1/2, and 4 to the n. Well, now it's similar, but what do we see? We see a -1 to the n over n to the 1/2. Now, it kind of looks like a p-series, except you have an alternating. So I say, oh, alternating. Okay, so alternating series, actually that's pretty helpful, because there's a very simple test for alternating series, and that is to say, if you alternate in sign, do you go to 0 and do you decrease to 0 monotonically? Well, yeah, n to the 1/2 goes to 0, and it does so in a very predictable way, which means this converges. So what does that tell us? It tells us 6 is in. All right, and so there's pictorially our answer, but I don't think they want a picture. I think they actually want to have an interval, and so we'll say, all right, our interval is -2 less than x less than or equal to 6. So here is our interval. And life is good. All right, so remember, if you're asked to find interval of convergence, 2 rounds. Start with your radius. You're going to use your root or ratio test. Ratio is almost always for factorials. Otherwise, I recommend root. Then check your endpoints. And you have to do each endpoint individually and figure out, is it in or is it out? And then put it all together. There you go. Free points, right? Well, no, it's not free. We got to do the work, but it's not so bad. Just take your time, do the process, you'll be good. All right, let's keep going. Number 5. We're asked to find S100, the partial sum of the first 100 terms of this series. And we're going from 1 to infinity, 4 over 4n minus 3, 4n plus 1. Okay, now, when we say S100, what we really are saying is, look, we're asking not from 1 to infinity, we're going to go from 1 to 100. And we're going to take 4 over 4n minus 3, 4n plus 1. And it says, give your final answer as an integer or a single fully reduced fraction. Now, the ignorant way to do this, which of course we're not going to do it the ignorant way, is to say, okay, great. I'll just write down 100 terms, and I will add them up. It's not going to fit on this page. There's lots of potential for arithmetical error, and so we're not going down that route. So what are we going to do? Well, we're going to try to get the right answer, and that's something I highly recommend. You should always try to get the right answer. You say, okay, so we're adding up sums. Now, when it comes to adding up sums, there's really two that we have a good, solid chance for. There's a third that we kind of have a chance for, but let's focus on the main two. And they are geometric sums and telescoping sums. Now, geometric sums are easy to spot. You're looking for nth power, something raised to the n. There's no nth powers there, so we know it's not geometric, which means we're looking telescoping. What's telescoping? Well, what we're going to do is write our expression in such a way that we see that things cancel. So we get cancellation going on. All right. So let's see what we can do. We're going to look at this and say, we want to somehow focus on an individual term. So we have this 4 over 4n minus 3 and 4n plus 1. What we'd like to do is somehow pull it apart. So you want to have like plus a little something and minus a little something. And so the goal is that when we look at consecutive parts, cancellation. So do we have a way to pull things apart? Yes, partial fractions. Good times. So we're going to have something over the 4n minus 3 and something else over the 4n plus 1 with a and b to be determined. Okay, so as we do partial fractions, first thing is recognize that we need it, and then we say, all right, now let's clear out our denominators. Okay, we can do that. And if we do that, what do we have? Well, this becomes 4 is equal to a times the 4n minus 3's cancel, so we have 4n plus 1. And then here the 4n plus 1's cancel, so we have b 4n minus 3. All right, now we have to, there's a couple of ways we can do this. We can expand and gather coefficients, or we can make good choices. And I like making good choices. And okay, so what are some good choices that we can make? Well, we could make a choice. How about n equals here negative 1/4? If we plug in negative 1/4 here for n, we'll see we get 0. So then that tells us that 4 is equal to a times 0, which just goes away, b, and negative 1/4 times 4 is negative 1 minus 3, so times negative 4. Okay, so b is negative 1. All right, well now we can come here and say, well, what about n equals 3/4? Okay, well again we get that 4. 3/4 times 4 is 3 plus 1 is 4, so 4 is 4a, and then that goes away, so that says, oh, a equals 1. All right, so what's all of this telling us? Well, all of this is to tell us the following, namely that our sum that we're after, which is our sum from 1 to 100 of 4 over 4n minus 3 times 4n plus 1 is equal to our sum from 1 to 100 of, now a is 1, so 1 over 4n minus 3 plus b, which is a minus 1 over 4n plus 1. All right, now comes the fun part. we write down terms. And so we're going to write down a couple terms at the start so we see the pattern and go until we hit the end. We're not going to write down 100 terms here, just a couple at the start and one at the end. So, okay, start with 1. So we have 4 minus 3 is 1. So this is 1 over 1. And then 4 plus 1 is 5. So minus 1 over 5. Plus, all right, now plug in 2. 8 minus 3 is 5, so that's 1 over 5. 8 plus 1 is 9. Subtract 1 over 9. Now, let's do one more. Then it will be convincing for us. So now we say, okay, 3. 12 minus 3 is 9, so 1 over 9. 12 plus 1 is 13, so 1 over 13. And we're going to keep going. So this is 1, 2, 3, and we stop at 100. So it's 1 over 400 minus 3, that's 397. 400 plus 1 is 400 plus 1, 401. Okay, now the great and what's the great is telescoping. We get things collapsing. And you say, hey, see how you have a minus 1/5 and a plus 1/5, a minus 1/9 plus 1/9? Well, that pattern's actually going to continue. So the minus 1/13 will actually cancel with the next term. This 1 over 397 will actually cancel with the term before. And so almost everything cancels. Almost. What doesn't? Well, the only things that don't cancel, and maybe we should make some notes. Cancel, 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 cancel. I almost feel like telescoping feels like cancel culture, right? It's like, okay, everything's getting canceled. All right, so, well, all right, what didn't cancel? What doesn't cancel? I can speak English. The term at the start and the term at the end. And now, instead of having to add up 100 terms, we have to add 2. Well, we're not done yet because we can't leave it as 2 terms. We have to get it down to 1 term. Say, okay, well, that's not too bad. Common denominator would be 401. So 401 over 401, subtract 1 over 401, leaves us with 400 over 401. And we're done. Whew. Good, good. All right, and all right, so there we go. So when you're faced with a sum where you actually have to add, look for geometric or telescoping. Now, the third thing that might show up is Taylor series, but oftentimes that shows up in different contexts. And so, all right, well, another successful problem, but still some more problems yet to come. Number 6. For each of the following series, we determine whether the series converges absolutely, conditionally, or diverges, and we circle our answer. And no justification is required. The sweet, sweet words, no justification is required. Okay, so we could make this really quick and just guess randomly, but that's a dangerous strategy. So let's actually reason. And so we're going to talk through. We're not going to write too many notes here, but let's talk about what's going on. So we'll start with the first one. Never worry about where your sum starts, because again, the first few terms don't matter. Focus on the end. So what do we see? There's a minus 9 to the n and 3 to the 2n. Now we say, hey, wait a second. 3 to the 2n, that's the same as 3 squared to the n, which is 9 to the n. So we're like, what? Well, that's saying, hey, what we really have going on with this sum is there's a negative 9 to the n upstairs and a 9 to the n downstairs. So, well, that says that the first sum looks like 2 to infinity of what? There's a negative 1 to the n over log n, because the 9 to the n's cancel out. Now we say, hey, alternating going to 0. And good. So that rules out divergence. So it converges. But we're not quite done. We know it converges, but does it converge absolutely or conditionally? Okay, so this converges. Cool. But what if we took out that minus 1 to the n, 1 over log n? Well, the problem is log n is very slowly going to 0. And we can compare it to 1 over n. Well, 1 over n diverges, but 1 over n is going to 0 faster than 1 over log n. So this diverges. Okay, so with the minus 1 to the n, we're converging. Without the minus 1 to the n, we're diverging, which means we are conditional. Okay, so the first sum is conditional convergence. All right, now our second sum. I see lots of pluses going on. When there's lots of pluses going on, what do? Well, we say focus on the main parts. Get rid of the noise. And you say, okay, now let's look at in the upstairs. You have number, root n, n squared. Which one's important? Well, the answer is the n squared is important. Okay, so ignore the other stuff. How about downstairs? Log of n to the 5th, n cubed, 10 to the 6th. Now, 10 to the 6th is a big number, but it's just a number. Okay, so that's not the important part. Now, this n to the 5th is a red herring because it's inside of a log. See, I could put the 5 down here. 5 times 2 log n, that's really log n, right? 10 log n. And log n grows much slower than n cubed. So you say, okay, so really, this is behaving like 4 n squared over n cubed. In fact, the 4 doesn't really matter. But the punchline here is this is sort of like comparing it, and this is what you would call limit comparison. We'll even put a LC here, limit comparison, of 4n squared over n cubed. Okay, so that's for some 1 over, sorry, n equals 1 to infinity of 1 over n. That's the harmonic sum. That diverges, so our sum diverges. Okay, cool. All right, well that takes care of 2 of our sums. Let's try another one. What do we see? Well, we see 2 things. N plus 2 over n cubed minus 2, 10 to the n, or 15 to the n. Now, you got to be a little bit careful here. We can't say, okay, what's the right growth? Because it's not fraction over fraction, right? It's piece. So let's think about each piece individually. Now, for the first piece, what is it looking like? Again, ignore the lower order terms. And it's looking like a sum 1 over n squared, which is p series. And we say, okay, great. That will converge. What about this part? Well, that's the sum of, we have 10 to the n, and then 5 cubed to the n. Now, 5 cubed is 5 times 5 times 5, also known as 125 to the n. And you'll notice 10 over 125 is small, smaller than 1. And so that converges. This is geometric. And so we say, oh, if you were to pull it apart, each one of them converges, no problems at all. There's no conditional. Each part converges absolutely. And so if you have 2 things which converge absolutely, put them together, they still converge absolutely. And therefore, life is good. Absolute convergence. All right. Now, how about our next sum? Cosine 2n over n factorial. Now, cosine or sine, you kind of look for one of 2 things. Either if you have like a cosine pi n, well, that's kind of there to be a hidden minus 1 to the n. If it's not a cosine, if there's not a pi on the inside, it's hard to hide a minus 1 to the n, and there's not. So there's a second way it shows up, which says, hey, remember it's bounded. So we say, oh, well, cosine 2n over n factorial in absolute value, because cosine is bounded between -1 and 1, it's at most 1 over n factorial. And the sum of 1 over n factorial, that's actually a really famous sum. It's e. Now, even if it's not a famous sum, you can figure out n factorial goes to 0 super quickly. Ratio test, whatever you want to throw at it, it converges. And you say, oh, well, look, since the absolute value is bounded by something which is absolutely convergent, then the sum is absolutely convergent. Okay, so cosine, you either say, is there a hidden plus minus thing going on, or is it just saying, look, I can bound everything in size? Okay, so this was a bound everything in size. All right, now, -1 to the n plus 1, alternating. Now, people often say alternating, okay, I'm going to circle condition. No, don't do that. Let's look at our terms. N factorial over log n. Well, hey, wait a second. N factorial is super big, super huge. It grows really, really fast. Log n is, it grows really slow. So you have something that's super big over something which is not small, but growing very small. Who wins the race between n factorial and log n? N factorial wins it by a mile. So your large stuff is on the top. What is that telling you? Well, it really says n factorial over log n is going to blow up. And so we have alternating signs, yes, but this part's not going to 0. It's getting huge. And in particular, since the terms don't go to 0, that says we must diverge. And there we go. Conditional, divergent, absolute, absolute, and divergent. And there's the reasoning. All right, good. One more problem to go. So let's take a look at that last one. Number 7, our final problem. Woohoo! We made it to the end. All right, and my goodness, there's a lot of parts to it. So, all right, we'll just very patiently work it through part by part, making sure, of course, we answer everything. Okay, so part A. Rewrite f of x 1 over 2 plus 3x in the form a over 1 minus r, and specifically identify a and r. All right. Well, we say, okay, what do we want? Well, we want to make it look like something over 1 minus r. Now, I'm going to key in on this 1. Say, well, I want to make this 2 somehow look like 1. So how can I make 2 look like 1? Well, I can do it. I could subtract 1, but no, we don't want to add terms. That's not going to help us. Instead, we can multiply by 1. So, multiply by 1/2. So what we can say is that, oh, this 1 over 2 plus 3x, we're going to multiply top and bottom by 1/2. And if we do that, we have 1/2 over 2 times 1/2 is 1. And then we have plus, and here 3 times 1/2 is 3/2 x. And so we're like, okay, we're really close. There's just a tiny problem. The minus sign. You see how it's a minus on it? And right now we have a plus. Well, that's okay. We can make pluses look like minuses. We have the technology. So this is the same as 1/2 over 1 subtract a negative, minus 3/2 x. And so we say, okay, so here's the form, and it says specifically identify a and r. So a is this top part is 1/2, r is this part, negative 3/2 x. All right. That's part A. Part B. Okay. Use your result from part A. Okay, so there's part A. To write the Taylor series for f of x centered at 0. Your Taylor series must include a formula for the nth term. Now, what's the Taylor series? Now, normally, you'd say it's the sum n equals 0 to infinity of, you take the nth derivative, evaluate at 0 over n factorial. And, of course, the reason I put in 0 is because we're centered at 0. And then we times it by x minus 0 to the n, x to the n. So you're like, oh, we got to take derivatives. We don't. You see, here's the thing. If we have a series, it's the series. And so we're like, oh, okay, well, do we have something for a over 1 minus r? We went through all this work. What can we say about a over 1 minus r? Well, it turns out a over 1 minus r is something very particular. This shows up in a special case of what's known as geometric. So it's a geometric series. So in particular, if you take the sum from n equals 0 to infinity of a r to the n, then you get a over 1 minus r. So the a is the first term, so that's when you plug in 0, and then the r is what you're multiplying by each time. So we say, oh, well, since we have a over r to the n, then what we'll do is we're going to plug in and say, hey, this is geometric, n equals 0 to infinity. And now we have our a, which is 1/2, and r to the n, minus 3/2 x to the n. And so this is our sum, n equals 0 to infinity. Well, we can put minus 3 to the power n. That's the upstairs. Downstairs we have a 2 and a 2 to the n. So that's a 2 to the n plus 1. And then we have x to the n. And this is a series that works. So since it's a series, it's the series. So, aha, life is good. So we save ourselves a lot of work. And in fact, we suspected that we shouldn't actually take derivatives because we didn't have any space. So this is one of our great things, which is to say, when you have a collection of your basic series that you know, we can build new series by manipulating old series. So that's why you want to have your geometric series down, your your sine, and your cosine, so that you can say, oh, let me manipulate the ones that I already know instead of starting from scratch every single time. Okay, so that's part B. Cool. Okay, now part C. Find the interval of convergence of the Taylor series you found in part B. Okay, so here's where again we say, let's not start from scratch. We know how to do this because we say it came from a geometric series. So the rule for geometric is what? So geometric converges when absolute value r is less than 1. And that's as simple as that. If you're building off geometric, you know when that converges. You say, okay, well, in our case, we know r. So that says we need negative 3/2 x in absolute value to be less than 1. Well, of course, you can pull out the negative 3/2, and that says 3/2 times absolute value of x needs to be less than 1, which says absolute value of x has to be less than 2/3, or if you like, negative 2/3 less than x less than positive 2/3. And there's our interval of convergence. And again, see how we're not doing a lot of work? Because we're using our knowledge. That's why knowledge is so awesome. It's like we invested time in the past, and now it's paying off. Ah, this is cool. We should do this more often. Okay, so one more part D. Write the Taylor series for g of x, which is minus 3 over 2 plus 3x squared, centered at 0. Now, but there's a hint. find f prime of x. Oh, okay. Well, we know that's f of x. So we say, okay, if f of x, I can write this as 2 plus 3x to the minus 1. Then f prime of x is the minus 1 comes down, 2 plus 3x to the minus 2 power, times by the derivative of the inside. So the derivative of 2 plus 3x is 3. So that gives us a minus 3 upstairs and a 2 plus 3x squared downstairs. Okay, that's f prime. That's also g. What? So what's the punchline here? Well, the punchline is if we have f, we can get g. So we say, okay, so we have the following. So g of x, which is f prime of x. Okay, well, that's the derivative. We know what f prime of x is. It's our series we found in part B. So that's the derivative of the sum, 0 to infinity, minus 3 to the n, 2 to the n plus 1, x to the n. All right, well, what's that? Now, the nice thing is you can pass the derivative through the sum. So this is the sum, n equals 0 to infinity of minus 3 to the nth power, 2 to the n plus 1 power, and the derivative of x to the n is n x to the n minus 1. Now, in some sense, that's the answer. We're going to go ahead and do one more tweak, and just because, well, they didn't really specify to do this, but I am suspicious. Usually when we talk about Taylor series, we want this to be x to like the nth power, not x to the n minus first power. So we're going to do one more small thing, which is we'll reindex. So I'm going to let k equal n minus 1, which is the same as saying n is equal to k plus 1. Now notice here at n equals 0, you get 0, so we really are starting our new sum at 1 because the 0th term drops out. So this would become the sum. When you plug in n equals 1, you start at 0, so k equals 0, and infinity minus 1 is infinity. And okay, so now n is k plus 1, so we have minus 3 to the k plus 1. Then downstairs, n plus 1 would be k plus 2, so 2 to the k plus 2. N is k plus 1, x to the n. So again, either one of those would be a great way to write the answer. And we're done. We're done. Ah, what a fun way to finish up. It's nice to end on a good note, right? And all right, well, again, I believe in you. You can do this. I know that this is oftentimes seen as a challenging test because there's lots of new ideas. And one of the biggest challenges is, of course, it's not just a matter of like, and the number is this, it's why. You have to think about the why, and you have to know your test. So practice your test, know what they say, and also what they don't say. And of course, keep doing the work. You'll be good. You'll be fine. I believe in you, and I hope I get to see you again. Bye.